In this video, we talk about polar and spherical coordinates. In 2 dimensions, we commonly use rectangular coordinates. We draw 2 perpendicular axes. A given point in the plane can be specified by 2 numbers, its horizontal and vertical projections onto the axis. These positions are called x and y, and constitute the rectangular or Cartesian coordinates of the point. An alternative 2-dimensional coordinate system is a polar coordinate system. Instead of using x and y to specify the point, we can use 2 other numbers. One is r, the radius, which is the distance from the origin of the coordinate system to the point, and phi, the polar angle, which is the angle of the horizontal axis in counterclockwise rotation sense. R and phi constitute the polar coordinates of the point. R is always positive, and the phi coordinate is periodic. A phi of 360 degrees is the same as a phi of 0 degrees. All points with a constant r but different phi form a circle. Interconversion between the 2 systems is simple. In one way, r equals the square root of x squared plus y squared, and the tangent of phi equals y divided by x. In the other direction, x equals r times the cosine of phi, and y equals r times the sine of phi. When do we use which coordinate system? We pick the one that makes the mathematical description simplest. So, if we are dealing with a rectangular problem, such as a particle in a 2D box, we use the rectangular system. If we are dealing with a circular box, or we're interested in rotations, we use the polar coordinates. Integrating over all space, that is over the entire plane, works the following way. In rectangular coordinates, the integral reads integral from negative infinity to positive infinity, and same again from negative infinity to positive infinity of whatever function you're dealing with, times dx dy. dx dy is called the infinitesimal volume element, dv. In spherical coordinates, this is the integral from 0 to infinity, positive infinity, and the integral from 0 to 2 pi of whatever function is given as a function of r and phi times r d phi dr with the volume element dv. The first integration goes from 0 to plus infinity for r, and the second goes from 0 to 2 pi for phi. Integrating over a circle with radius 1 can be done with the following simple integral. Integral from 0 to 2 pi of the function that's going to depend on phi times d phi. These 2 coordinate systems easily generalize to 3 dimensions. The 3D rectangular system contains 3 mutually perpendicular axes. A given point is specified by its projection on the z-axis and by its projections onto the x and the y-axis. X, y, and z constitute the rectangular coordinates of the point. The other 3D system is the spherical coordinate system, which specifies the point by its distance from the origin, r, and by 2 angles. One angle is down from the z-axis and is called theta, and the other angle is the angle between the x-axis and the projection of the r vector down into the xy plane, and it's called phi. Theta is called the inclination and runs from 0, that's when it points up at the North Pole, to pi when it points down to the South Pole. Phi is called the azimuthal angle and runs from 0 to pi after a full round. All points with identical r but different theta and phi lie on a sphere of radius r. Conversions between the 2 coordinate systems are as follows. To transform rectangular to spherical coordinates, use r equals the square root of x squared plus y squared plus z squared. Then the cosine of theta equals z divided by r, and the tangent of phi equals y divided by x. To obtain x, y, and z from the spherical coordinates, note that the projection of the r vector onto the xy plane, that is this here, is equal to r times the sine of theta. With this we get x equals r times sine of theta times cosine of phi, y equals r times sine of theta times the sine of phi, and lastly z equals r times cosine theta without a phi dependence. Again, the decision of which 3D coordinate system to use boils down to which one gives simpler mathematical expressions for the given problem. This is usually the one that matches the symmetry of the problem better. So, for example, for a cubic box, rectangular coordinates are best, but for problems with spherical symmetry, such as an atom or a nanoparticle, the spherical coordinates are preferred. We often have to perform integrations over all space. In Cartesian or rectangular coordinates, it's simple. Integral from negative infinity to positive infinity 3 times. Of whatever function is given, so function of x, y, and z, times dx, dy, dz, which is the infinitesimal volume element, dv. In spherical coordinates, the corresponding volume element is different. The integration there reads integral from 0 to plus infinity for r, then the integral from 0 to pi for theta, and the integral from 0 to 2 pi for phi of a function f of r, theta, and phi times the volume element, which is r squared sine theta dr d theta d phi. Watch out for this volume element. And do not forget the prefactors r squared and sine theta. Integrating only over a sphere with radius 1 can be done with the following integral. Integral of theta from 0 to pi, and the integral from 0 to 2 pi for phi of some function f of theta and phi times sine theta d phi d theta. Be careful again not to forget the sine theta factor in this integral. In summary, you can use either rectangular or polar or spherical coordinates. The right choice depends on the symmetry of the problem. Also, when integrating in polar or spherical coordinates, watch out for the additional factors in an integral, r squared sine theta for volume integrals and sine theta for area integrals over the sphere.